One was you had something on a slope. Was it a box? Are you guys there? Who's there now?
Yes, miss.
Yeah. It was a box, right? Had I given you the angle here of the slope? Some theta? And the other one was an object, maybe a particle on a, there was pulley here.
This is how it looked, miss.
Correct,
Miss?
Yes?
This is how it looked.
Oh, wait. I can't see. Wait. Ah, right. Okay. Yeah. So I've drawn it in the other direction. I hope that's fine. So I draw it. It's the other direction. Okay. Right. So the free body force diagram for this. So, okay, you have it like that. Okay. So you would have the weight acting from the center of gravity downwards. Weight is always vertically downwards. This, you might be on a slant surface, but your weight be acting vertically downwards towards the earth, right? So that's your weight. But your reaction force from the slope would be perpendicular to that surface that you are standing on. So that would go like that, perpendicular. Your reaction force, your normal reaction force would be perpendicular, and the angle between these two would be theta. And I said that this was rough. I said that it was rough. It has to be rough, otherwise this would, if you keep an object on a completely smooth surface, slant surface, it will start sliding down. So what is keeping it, it's at rest now. What is keeping it still? It's the friction acting upwards, because it's trying to move down. It is not moving yet, but it's trying to move down. Who's keeping it? Who's stopping it? Friction. Let's say friction. There is no standard like symbol for friction force, and it has to be marked on the, like the edge, because it acts on the surface, the base. So these are the three forces. That's all. Anything else? Did you mark anything else on this diagram?
No, miss.
Okay, so that's it, right? And then for that one, let me move this here. Let me minimize that altogether. So this was the object in focus. I wanted you to draw a free body force diagram for that object. So, okay, you start with weight. And normal reaction. These two are in one line, the line of action. Yes, Hatfi, the normal reaction force is always perpendicular to the surface on which the object is resting. That is why it is called normal reaction. The word normal is to say the meaning there is perpendicular. You know, normal means perpendicular. That's why it's called normal reaction, because that reaction, this R, is always perpendicular to the surface you're on. Remember in the ladder example, the reaction from the wall was perpendicular to the wall. The reaction from the ground was perpendicular to the ground. It's always perpendicular. So here, this is on the table, the reaction would be perpendicular to the table surface, tabletop. And the line of action is the same for the weight and the reaction. Same line of action. It's not like that. Weight coming here, reaction, same line, along one line. And then there are two masses hanging via a string, via two strings. So there will be two tensions. There would be a tension that way, it will be pulling that way, and this will be pulling this way. So since we don't know, I mean, we don't know whether they're equal or what, so you can say T1 and T2, they are both tensions, but in general we say We don't know whether they are equal or this different. So we'll mark them different, T1 and T2 maybe. Tension 1, tension 2. Did I say that one was heavier and this was rough or anything like that?
You said the table was rough. You didn't say which one was heavier.
Okay. So suppose this is heavier. Suppose this is heavier. Then this
And
is trying to move
Miss,
that way.
This you said that it's heavier.
yeah. You said that
Because
it's moving that. You said that it's moving
I
that
said
side.
it was moving that way. That means
Yeah.
this is heavier, right? Then there would
Okay.
be also friction acting here. In what direction?
In the opposite direction of motion.
And where do you mark it? Down here.
Downward.
Different line of action. So this is friction.
Miss,
Yeah.
aren't we supposed to mark the direction of motion also?
This is just a free body force diagram, so you don't have to do that.
Okay.
You have to mark the direction of the motion if when you are applying F equals ma. But it's a good practice. I would not say anything if you have marked the direction of motion like that. It would act
Okay.
that way. So the motion arrow, we show the motion with an arrow. A double arrow means it's accelerating, and that arrow you have to place outside of the object. Notice that the force arrows are all passing through the object, they're acting on the object. So to differentiate between the force arrows and the motion arrow, if you show it on the object, it would, one might get confused whether that's another force. So that's why I even used a different color. This is just to show the motion. Okay, you place it outside of the object, it's moving that way, right? Today we will learn. Now what you saw here is that all the scenarios I gave you here were natural scenarios, things that you see around you, things on a things kept on a table, things on a slab. I mean, these are things that you see around you. What you have to notice here is that on a certain object that you see around you, there is always more than one force acting. Did we have a single object? Check all your free body force diagrams. Did we have a single object on which only one force acted? Never. You look around you and see whether you can find one object on which only one force is acting. You won't find it. Right, you won't find any objects like that. At least there will be two forces acting on any object, because the weight is always there. No, weight is always there. And in addition to it, if your object can't be just floating in air, right? It has to be on something, then there will be a reaction. At least reaction is there. And then there could be these other, if it is moving, there will be friction, air resistance, and all these other things. Usually air resistance is neglected. You will not get any questions where air resistance is involved. Okay, what you have to learn. So since there are more than one force acting on an object all the time, an interesting question to ask would be, what is the net force acting on an object? We would want to know what's the uh, overall effect of these forces. What's the net? What's the can we add all the forces and get the resultant force? It's called the resultant force. So for that, so our next topic is how to find the resultant force acting on an object. Resultant means the total of all the forces acting on an object. Since forces are vectors, finding the resultant is not just adding them all together. If you were just adding some masses, if you wanted to find the total mass of something, you would add the masses because they are scalars, they don't have a direction involved. uh, 2 kilograms plus 5 kilograms plus 7 kilograms, you just add the numbers. But if you are adding forces, you have to know the direction. The direction matters when you are adding them. For example, two forces acting in the same direction would add up, but two forces acting in opposite directions would, one would cancel part of the other. If they are the same, they will cancel off each other completely. So the direction would give you a minus sign, things like that. I mean, opposite direction would give you a minus sign. So we have to know how to find the resultant force when there are more than one force acting on an object. So your next topic is finding it's called resultant force, resultant. Another word would be, a more familiar word might be net force, the net force, Finding the resultant force acting on an object, acting on an object. Let's say now acting on a point object. We are considering, now you saw that these objects had a dimension, some dimension, right? It has a length, width, it has a size. But when we mark forces acting on an object, we think of the object as a point, so that all the forces are passing through that point. Otherwise, you can't find the resultant on a point object. So let's consider some different cases. Number one, when they're acting in the same direction, or a bullet point acting in the same direction, forces acting in the same direction. You know that if they're acting in the same direction, you can simply add them. So for example, here's your object, point object, and you have one force acting 4 newtons and another force acting in the same direction 7 newtons. What's the resultant? This is equivalent to having just a single force in that direction. So to indicate the resultant, I'll put a big arrow like this with a red arrow. That means what I'm saying is that these two forces can be replaced with this single force. This force is equivalent to having these two forces. What would the size of that force be? 11 newtons. You simply add them. 7 plus 4, 11 newtons. So if forces are acting in the same direction, you simply add them to find the resultant. Write with me and stop me if you have any doubt. Then if you have forces acting in opposite directions, forces acting, so I have shown you for 2 forces. If you had 10 forces, same thing, you add all of them, As long as they are acting in the same direction, you add them. Forces acting in opposite directions, TE, opposite. So it could be left and right, up and down, some angled direction, but in the other one is in the other opposite direction. So any 2 opposite directions. So I would draw, for convenience, I would draw 2 horizontal ones. So say you have 4 newtons this way and 7 newtons that way. Let me know if my video thumbnail is covering anything that I'm writing. Okay. So this would be equivalent to, this scenario is equivalent to having just as what single force? I can replace these 2 with what single force? 3 newtons acting this way. So the resultant of these 2 is 3 newtons. What you have to notice here is it's the same 2 forces, 7 newtons and 4 newtons, but their resultant is different depending on how they act, because the direction matters. So here the net force is 11, here the net force is 3. What if forces act perpendicular to each other? Forces acting perpendicular to each other. So say you have your point object and the 2 forces are acting perpendicular to each other. So I'll use the same 2 forces, say 4 newtons this way and 7 newtons this way. Oh, sorry, 7 newtons this way. right? Perpendicular, any two perpendicular directions. I have shown this way, it could be like that, any two perpendicular directions. Then the resultant, it's quite obvious that the net force. Now imagine you have an object and you pull it this way with one force and pull it that way with another force. In what direction would this move? It would move in between somewhere, right? That means the net effect is in between. um, if the two forces were equal in size, it would directly move right in the middle line. But now in this, you have to see that it would be more towards the bigger force. Can we find the exact angle in which it will move is a question that you can ask. We can find it. How do you find the size of the net force? It's clear that the net force would go between these two forces, right? I mean, if you have two, now, for example, in this case, this object would start moving in that direction. In this case, this object would start moving in this direction. In this case, this object would start moving in that direction. This is a consequence of Newton's first law. We will learn that after we do this. An object will accelerate in the direction of the resultant force. It's very obvious, of course. If there is a net force acting in a certain, you might have 100 forces acting on you, but what will determine your movement is the net force, not the individual 100 forces. Some of them will cancel out each other. So you find the net force, and if there is a net force in a certain direction, you would start accelerating in that direction. Okay, a resultant force always accelerates an object, not just move, accelerates. It will speed you up, right? So how do you find that? What's the size of this? So this follows from a geometrical concept, because forces can be represented with arrows whose length represents their size. So these two forces I can show. This could be a line that is 4 centimeters long, for example, and that could be a line that is 7 centimeters long. They are perpendicular, and the resultant force is given by, this is called Parallelogram Rule. You're not learning the rule, but the resultant is given by the Pythagoras Theorem. Okay, so the resultant here is square root of 7 squared plus 4 squared, which is how much? Use a calculator and tell me. And you can exactly tell the angle here, or this angle with the vertical. One of the angles, the angle with the horizontal or the angle with the vertical. You can exactly say in what direction it's moving. You can give tan theta. You can find theta by doing tan theta. What's the answer for that? Tan theta is because if you, I will draw a little.
Miss, that is square root 65.
Good. Square root 65.
Square root 65 is Newton.
Newton.
Then tan theta.
Tan theta would be, so it's like that. If you think of a right angle triangle, if I just draw, I don't want to mess this diagram, but if you draw like this, this can complete a parallelogram. And if this is theta, it is opposite over adjacent. So if this is 7 long, this would be 7 long. So it would be 7 divided by 4. So y direction force divided by
60.3.
Yeah, so it's y divided by x. So it's 7 divided by 4. Right? So theta is tan inverse of that. So you can exactly find that angle also if you want it. So this is the basic. Acting in the same direction, acting in opposite directions, acting perpendicular to each other. What if there are forces acting at other angles? Like two forces acting, one acting this way and one acting 30 degrees to it, not 90. Then how do we do it? Then we have to, we have to resolve the forces. into components. This is something you have learned before. So I will straight away go into it. Your third bullet. Sorry, fourth bullet, no? Forces acting at different angles, any other blah, blah, blah angles, different angles. The strategy that you do here is, if there is, now, as you saw here, we prefer these two directions, the horizontal and the vertical directions. We like it if our forces act in those directions, horizontal and vertical. But if you have some force acting at some other angle, you can resolve it to two components. Any force can be resolved into two components. What that means is that any force that is acting in a certain angle can be replaced with two components acting vertically and horizontally. Okay, so in this, we resolve forces in vertical, and actually you don't have to stick to resolving them into vertical and horizontal directions. It's just a preference that we have. So that's why I'm giving it, but it can be done in any direction that you want. In this, we resolve forces in vertical and horizontal directions. And when you do that, all your forces would be acting along the horizontal line, acting along the vertical line, and you can use the previous three ways in which we added forces to find the resultant. So we'll say, in this, we resolve forces in vertical and horizontal directions and use the above three methods, to a combination of three methods. If you have a couple of them in acting in the same direction, you add them, opposite, you subtract them, perpendicular, Pythagoras. So you use the above three methods, a combination of above three methods to find the resultant. So let's take an example. Here's your point object.
Miss,
Yes. Oh, hi, Mihail. Who's talking now? Is it Mihail? No one is talking. Let me give you a lot of forces. Say one in that direction, 3 newtons. One in a direction like this. Oh, can't hear. Can you hear me now? I didn't do anything. Oh, even your...
I can't. Your hand is stuck. I don't know. Both videos are stuck.
I can, like, from my end, I don't see anything. But your voices are very... let me try. Do you hear me now?
Yeah, it's happening for quite long.
I can't hear you well. I can't hear you well.
Miss, everything for me is lagging. Everything is lagging.
Oh, Hatri is saying it has been happening for quite a long time. Let me try changing the... okay. Let me try changing the router. You didn't get anything? What do you mean, Hatri? You didn't get anything? You couldn't hear anything? Let me change the router. Oh no, I can't change the router because somebody just came to fix that router. Oh, I'm so sorry. Oh, so sorry. Disconnect. How is it now? Hatri, how is it now? Guys, are you all there? After the perpendicular,
Much better.
much better?
Miss,
Yeah.
I thought that it was my problem.
Much better, miss.
Oh, I'm so sorry.
Yeah.
Yeah, okay. Okay, so Hatri says after the perpendicular forces, it wasn't clear. Wow, so did you not hear?
Miss, still,
Is it still there?
Miss, you were fast. Like,
I mean, it must have gone.
fast forward.
Yeah, fast forward, like, oh, wow. Okay.
Yes, miss, you're forwarding.
Is it okay now?
Yeah, now it's fine.
Now it's fine. Okay. So I was just saying, so you must have missed what I said here. Whenever you have forces acting at an angle, not in the horizontal direction and the vertical directions, but at an angle in between, you can resolve them into two components. Okay? Resolve into components. We usually resolve them in the vertical and the horizontal direction. So I'm going to take an example and show you. I'm sorry that there is a noise here. Somebody just came to fix the router. So shall we just copy the diagram? Okay. Say you have 3 newtons in that way, 8 newtons this way. So I will just show with the dotted lines. I'm showing with dotted lines, the vertical and the horizontal. And say I'll put another force like in that direction. Okay, say 5 newtons. Five newtons. I'll give you the angles. Say this is 30 degrees, and say this is 20 degrees. 20 and 30. Okay, let's do these three. Sorry about the noise again. So what you have to do is you keep the forces that are already in the horizontal or the vertical direction. I have one force in the horizontal direction. You keep it. You keep it as it is. The forces acting at an angle, you split into two components. This is called resolving a force into components. Okay. I hope you are familiar with this. This 5 newtons force can be thought of as having two components, one in the vertical direction, one in the horizontal direction. So when you split that, it will have two components, like it's at an angle like that. Okay, it will have two components like that. You kind of open it up in a vertical and a perpendicular direction, vertical and horizontal direction. And how do you find? It's like it's the reverse of now. When you did two forces acting perpendicular to each other, you found the resultant by using Pythagoras. This is the reverse. If you think of that, this is the resultant of two forces. What are those two forces? It's going back. So what you do is, this is how you get it. If this is 5, can you tell me what this is? You already know this, I'm sure. This is 5. It's cos and sine. This is what? 5. I will draw a small diagram here.
5 sine.
5
Cos, 5 cos. This is how you get it.
cos.
It's the vertical one or the horizontal one?
No, it depends on where the angle is. The angle 20 is here.
Yeah, that is 5 cos 20.
Remember it like this. If you are closing that angle to come to your component, you have to close that. Close is cos. So closing 20, 5 cos 20. This is 5 cos 20. I will show you how this happens, but that's a way to remember it. And then the other one would be 5 sine. You open to some side, that is sine. 5 sine 20. And then the two forces, the two components of this, it'll have one this way again and one that way. Right? This would be 8 what? Because you're closing when you come this way, 8 cos 30, and this would be 8 sine 30. If you want to know why this is cos and sine, where did that come from? It again comes from the same diagram. I'll draw it in a little bubble like here, especially for Hatfi who do not do these in anywhere else. You don't do physics, no, Hatfi? So it comes from a triangle. So say this is your 5 newtons force, and then I gave you this is 20. You can complete a right angle triangle. You're trying to find the length of this, because forces can be put into a geometric diagram, because a force can be represented with a line whose length has the size of the force. If this is a line 5 long, this is 20, the length of this would give you the component. So this, how do you find this? If I call it x, you can do, I know this is 5 long, this is, I want to find this is 90 degrees. You can do, what is that? Cos 20 is equal to x divided by 5, and x is 5 cos 20. That's how you got that. And then when you want the other component, that is this, it comes here, that is same as finding this, that would be sine. Okay, so it's a little mathematical thing going on there. So you remember it like if you are closing the given angle, it's cos, other side is sine. One is cos, one is sine. Right. Now, this is better than this, right? Now, the 3 forces we have, there are more forces here, but they're all acting in the horizontal and vertical direction. So you can just, by doing addition and subtraction, you can quickly simplify this. Let's simplify this further. This is same as what? How do you, now I'm trying to find the single net force, single resultant force. I have to add all of these together. I can add these two, right? They're acting in the same direction. I can add these two, and these two can be subtracted, like whichever, the bigger one minus the small one. And these two can be subtracted. So what we usually do is, can you find the sizes of these? Who can give me the sizes of these? How much is this? This is 4. No, this is 4. How much is this? How much are these? What is 5 cos 20? Give me to the nearest, let's take to the first. The nearest whole number.
Wait, well, whole number, that would be in 5.
So I'll put approximately equal, because I'm not paying attention to the numbers here. Just understand the concept. So that's why I'm avoiding. How much is that?
5, miss.
5, okay. Approximate. Now it's 5 point something. This one?
That would be 4 row 3.
No,
No, that one. Sorry,
it
sorry,
is
miss.
5.
Sorry, miss.
Because it's
okay. Then should I give the point form?
Point. It
Should I
can't
give the
be
point
5.
form, miss?
It can't be greater than 5.
Okay, then it would be.
Think about it. Wait, Nathan. So this
Miss,
is.
shall I give?
Wait. Now, if you do a by mistake, you get 5 point something like that. Then you have to know that can't be. You have to know that. Why? It's the component of 5. Components are smaller than your original force. They are the components. The components combined to 5, right?
Then it would be 4.
4.
Yeah. Then if I'm giving point form, it's 4.698.
All right. Let's say for 4.6, and this is how much?
Then the 5.5 sine.
Yes.
sign, that would mean that is 1.71.
1.7. Okay. What is this? 8 cos 30.
8 cos 30, that would mean that is 4 root 3.
Give me to one decimal place. So there, these are all.
Okay, then 6.9.
Right? Do you see the components of 8 should be less than 8? It's 4 and 6.9. The components of 5 must be less than 5 because they combined into 5. Okay. Now, shall we now? So let's just focus on these numbers. So I had the 3n, original 3n, 6.9 here, 4 here, 1.7 here. Okay. Now let's quickly, okay, here's my object. If you combine the vertical ones, these two are opposite. 4.6, 6.9, I get something this way. How much is that? 6.9 minus 4.6, 2.3. And along this way, these two can be added. This is 5.7, and then that will be subtracted. You will get something this way. 5.7 minus 3 is 2.7. See whether you understand that step. So I was able to simplify these forces that were acting at different angles into two that are acting perpendicular to each other. Now I can use Pythagoras. So I can simplify this further to say, now I get my resultant. It's going to come in a direction in between these two. And it is square root of 2.7 squared plus 2.3 squared. And I can find the angle. That's the angle. And this is how much? How much is this?
Miss, number of newtons is 3.5 newtons.
That's
And the angle is 3.3 over, that would be 40.4. Yeah, 40.4.
okay. So you have simplified three forces acting at various different angles. So if you can do something like that, you can do anything. This is the procedure. This is the way to do it. Any slant force, you split into its components so that you have all the forces in just two perpendicular directions. They can be simplified by adding and subtracting down to something that looks like that, two perpendicular forces, and then you use Pythagoras. Okay, so that is that. Any questions from that?
No, miss. Understood.
Let's write a very important what can I call it? This is a consequence of Newton's first law, but I want to give it as a separate, like a little result. Okay, so write in red. Let me ask you first. If you have an object on which a couple of forces are acting, like a number of forces are acting, but the object is at rest. It's not moving, it's just at rest. But there are, like, say there are 10 forces acting on it. This way, that way, this way, that way, like a single point object, a point object, and there are so many forces acting like that, different forces. But it remains still. What does that tell you about the, oh, Hatvi says the angle is 49.5. Now you are the ones who are using the calculators. I am not, I don't have a calculator here to use. You have to do it correctly. You can't do a mistake. You can't make a mistake in a calculation. Okay. So if you have an object upon which there are several forces acting, but it is at rest, what can you say about the resultant force, the net force? What must it be? Can you just think on your own? No need to apply any, what did Newton say about? No, just think of if from your understanding about, you can feel it. If there are a couple of forces that are trying to pull me in all different directions, somebody's pulling me in that way, somebody's pulling me in the other way. Like I said, there are 10 people trying to pull me in 10 different directions. But if I'm staying still, what does that mean?
Resultant force is 0.
Resultant force is 0, right? The net force is 0. They must all get cancelled off, and the result is 0. So 10 forces have the result of 0. If that happens, you won't move. Another way to put this is like this. You can say that if you have an object that is not moving, it's at rest, then if you think of just any one direction, say I think of like any certain line, along any line, the total forces acting in one direction must be equal to the total force acting in the opposite direction. If you take any two directions, like along a line, opposite directions, the total in that way must equate the total in the other way. And it's true for any direction that you consider. If you find the total in that direction, that'll be balanced by the total in the other direction. That's why it's not moving. Okay, so let's write this. I'm putting it in a big in a box like that. Okay,
Miss, should we draw that?
not that. Let's write this result. I'm going to write in this red box.
Okay.
If an object is at rest, what does it imply? The resultant force on it must be 0. If an object is at rest, the resultant force on it must be 0.
Bless you, Miss. Bless you again.
Sorry, excuse me.
Bless you 4 times.
Miss, where do you live? So you no lockdown in your area,
No, Mali, don't worry. No problem.
right?
Just a sneeze because people are thinking here.
And I was just thinking. That's all.
Thank
It's okay. It's okay.
Answer. I know. I mean, I'm happy to hear. I'm happy to see that you're concerned. Okay. So I said that this is a consequence of Newton's first law. Who can tell me what Newton's first law is? I will, with one thing that I write here, actually 2 things that I write here, I can complete the Newton's first law in different words. Now, if I ask you to say it, Newton's first law, you will say it like a dua, like a gata, like a prayer, da 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 da. You will just recite it. Can you recite Newton's first law?
Miss, I don't know the tune.
No
Yes,
theory,
I.
sister.
Okay. It's when an object has zero resultant force, it's the object is considered to be either at rest or traveling along a straight line at constant speed.
Good. Did you just think about it and like formulate the theorem on the spot now, or was it a memorized sentence?
50-50.
50-50. Okay. Can someone else repeat or maybe say the way you have memorized it? Can someone else say it?
When net motion is zero,
Net motion.
when the resultant force is zero, the object is considered to be at rest or at constant motion or constant velocity.
Constant velocity.
Yeah.
Uh, can another person say it? Who else can speak? I think only the two of you can speak. Mihil, can you speak? No, Mihil can't speak now. Who else can speak now? Tarindu? Can any of the girls speak? Yes, Tarindu. Can you recite? I'm purposely using the word recite. I wanted to recite Newton's.
Miss, it's
I
also
just remember it as
Tarindu, you're saying?
I
Tarindu,
just
go ahead.
remember it as when the resultant force is zero, the object can either be at rest or moving at a constant velocity.
Uh-huh. So you are?
Miss, shall I tell Miss?
Yes, Nathan?
Newton's law states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by an action of an external force.
Okay, so you're reading it off.
Okay, that's a
Yes, sir.
recital. That's a recital.
Oh, what's that noise?
It's from your end, Miss.
Yeah, I know. Oh, I'm very sorry. There is a little bit of a chaos happening here right now. And okay.
No, it's okay, miss. It's
So you still
not really. It's not interrupting us.
okay. Now can you say that the first law in your own words? Now, can you explain it to me? Like, if I were someone if I'm someone who has never heard of Newton or any of this, just in lame, simple, plain words, what is it telling you?
So,
Now,
miss, then you don't know about resultant forces?
you can say net force. Net force is something. The word net, you say net salary. I mean, that's something that any person would know when you say net salary.
Ah.
So from that net force, if you say, I would know what that means.
Okay, so then if the net force of an object is zero, then that object is not moving, or it's either moving in a constant speed in a straight line.
Okay, so if the net force acting on an object is zero, you are saying either it should be at rest.
Yes.
If it is not at rest, if it is moving, it has to be moving in a straight line with a constant speed.
Yeah.
So it can't be moving in a curve at a constant speed? No.
No, because the velocity keeps changing when you go on a curve, because the direction changes every moment. Velocity is magnitude and direction. In a curve, even though the magnitude is the same, the direction changes every second.
So what needs to stay the same is the velocity, is that right?
Miss?
Velocity.
Yes, the velocity as a whole has
Miss,
to be.
can you repeat your question, because I'm getting kind of confused?
I want you to explain Newton's first law in your own words, as you are explaining it to a lay person, a person walking on the road. So okay, let me
Why
read.
would a layperson need the first law?
he might not need it. I'm just asking you to do it. So Biman,
He needs safety guidelines.
yeah, that's true. Biman is saying if an object is at rest, it remains at rest, or if it is in motion, it moves with constant velocity unless it is acted upon by a resultant force. So this is actually could be the perfect way of how Newton has stated it. Tarindo, do you want to say it?
No, Miss, it's okay.
Okay, it's the same thing. So now you all are saying what would happen to the object if the resultant force is zero. If the resultant force is zero, either it would be at rest or it would be moving at a constant velocity. What if there is a resultant force? Then what would happen? What if the net force is not zero? Then what would happen? Can you tell me an answer to that?
Then it's moving, but not at a constant speed, not at a constant velocity.
It would be definitely moving. If not at a constant velocity, what would that be?
Acceleration.
Acceleration. That's the complete Newton's first law. If the resultant force is zero on an object, if it is still, it will remain still. If it is moving, it will move at a constant velocity. If the net force is not zero, it will be accelerating. Okay, so I have written part of the law here. If an object is at rest, and the converse is also true. Converse, if you know that, now I'm telling the reverse of this. If you know that an object is at rest, then the resultant must be zero. If you know that an object is moving at a constant velocity, the resultant force must be zero. By the way,
Was that a drill?
wait. Give us 2 minutes. Here's some entertainment until until that is over. Here's some entertainment. Putta, can you entertain us? Really, brother?
What?
Say hello. Hello, Ayas.
Hello? Nothing.
No one.
Hello.
Hello.
Tell them that your name. Yeah, your name. Say it loud.
Can you do?
Pramindu. Okay. Drill ki varada. Malli. I think it's over. Just a one-time drill. Okay. So I was saying the reverse of this law. If you know the type of motion, you would know what the resultant force is, and vice versa. If you know the resultant force, you would know how the object is moving. If the resultant force is zero, it should not move or move at a constant velocity. If the resultant force is not zero, it must accelerate. And if you come this way, if you know something is not moving, resultant force is zero. If you know that something is moving at a constant velocity, you know that the resultant force is zero. If you know that something is accelerating, you know that the resultant force is not zero. There is a net force. Okay, that's the summary of Newton's first law. You don't have to say it like a prayer. So I'm giving part of it here. If an object is at rest, the resultant force must be zero. Since this topic is forces under equilibrium, we would just be considering objects at rest. Okay. In the next topic, when we talk about moving objects, then we will take the other two cases when it is moving at a constant velocity and acceleration. Okay. And okay, yeah. So let's do a question on this. Let's see how we can use this knowledge that we learned about finding the net force or the resultant force, and this rule. If an object is at rest, the resultant force must be zero. And can I add one more thing? So if the resultant force is zero, If the resultant force is 0, uh, there are two little formulas that you can apply. I'm sorry that I might have to go out of this box to write that other thing. If the resultant force is 0, upward forces must equal the downward forces, and leftward forces, rightward forces must equal the leftward forces. What I'm just saying here is that I have taken two directions, but along any line, the total acting in a certain direction must balance the total acting in the opposite direction if the net is 0. And that is true along any line. Just think about that. You really need to think about that to really appreciate what I just said. If an object is at rest, which means if the net force is 0, in any direction that you consider, the total in that direction must be balanced with the total in the other direction. That is why it is not moving. Okay, so complete that too. So this is sometimes called these two are like two formulas that you can apply. This is called vertical equilibrium and this is called horizontal equilibrium. If an object is in equilibrium, it has to be in equilibrium vertically and horizontally and in any other direction. It's equilibrium in any other direction. Okay, let's look at an example. Until then, you will not really understand this. Okay, can you do this question? This number 3, this one. So I will keep it here. You read the question, copy the diagram, and let's work on that. You copy the diagram. I will show you how to tackle this question. It says a particle in equilibrium, it's in equilibrium, has 3 forces, 5, 6, and F, acting on it in the horizontal plane. Find the values of F and theta. So can you copy this as an example? Write example and copy this. I will show you how you are supposed to tackle something like that, how to apply that the two little things I gave you, horizontal equilibrium and vertical equilibrium, the two like the formulas, how to apply that. Okay, so copy the question with the diagram. You can just copy the diagram and say, find the value of F and theta. That would be enough. I will show you how you can tackle a question like this. Can I remove the book? Can I take off the book? Can I take the book?
Okay, miss.
So I will draw the diagram here. Here's what you had, a point object, 5 newtons this way, some F force that way. This angle is theta, and a force this way, 6 newtons. This is 70. Okay, it's given that this is in equilibrium. So what you can do is you can consider the horizontal equilibrium and the vertical equilibrium. Okay, that is the last two, these two formulas. You can equate the total upward forces to the total downward forces and the total rightward to total leftward. Okay, it's so what you would say is that vertical, you can say vertical equilibrium. If you consider vertical equilibrium, total upward forces must equal the total downward forces. In physics, you might be doing this as you add all the forces in a certain direction with putting plus and minus depending on whether they are acting in the same direction or opposite direction and equal to 0. It's the same thing. So what are the upward forces acting here? There is nothing coming from the horizontal forces, no component from the horizontal forces. This is entirely horizontal. There would be a component, an upward component coming from this force. And what is that component? F, sine or cos. The vertical component of F is, this way is F, say it quickly.
Wait, miss, the vertical component, yes?
F
That
sine,
is F sine theta.
that's the only upward force.
F sine,
Then this
yeah, and equals to 6 sine
equal to 6
6 sine 70.
70. You get one equation from that. Now this equation has two unknowns, f and theta. So you need another equation to solve and find f and theta. So let's consider horizontal equilibrium. You can put an arrow in any direction. This means horizontal equilibrium. There you can do leftward forces equal rightward forces. Leftward you have only one force, 5. Rightward, you have a component coming from this and a component coming from this. So the sum of those two. So that would be F cos theta plus 6 cos 70.
It's cos 70.
Now, how to solve this is a different matter. How can we solve this? Something that is very commonly, that commonly happens in these questions is that you get sine theta in one equation and cos theta in another equation. Make f cos theta the subject here. If I make f cos theta the subject, f cos theta is equal to f cos theta is equal to 5 minus 6 cos 70. Now that is just a number. And then you can easily, if you divide 1 by 2, you get tan theta. And you can find theta from that. So you have to solve these two equations simultaneously. And a common way that you have to do it is by, if you can only do it if you have something similar to this. The same force that will get cancelled off here, and one sine theta and one cos theta. Then you can divide. 1 divided by 2 would give you tan theta. That is 6 sine 70 divided by 5 minus 6 cos 70, and you find this using your calculator. And tell me what finally theta is. So theta is tan inverse of this.
Theta is 64.2, 62.4.
62 point?
2.4.
62 point. See whether everyone gets that? 62. And once you have your theta, you can substitute that in any one of your equations and find f. This is the easiest substitute back. Put theta here and find f. Sub in 1 and you get f. Okay, what's f? So remember what we did here, okay? If you didn't notice that the f sine theta and the f cos theta here, then they could be divided to give a tan theta. If you didn't notice that, solving these two might be a little challenging because it doesn't have the normal form of a pair of simultaneous equations. F and theta are in the same term. The two unknowns are in the same term. They are not two terms. Okay, Hatvi says F is 6.36 newtons, correct?
Wait, miss, still doing.
Okay.
Correct, miss.
Correct. Okay. Now I will give you a similar one to do on your own. Similar one. Is everyone done with this? Can I take this away?
Yes, miss, correct answer.
Correct answer. This first question, quickly copy it and you do it on your own. It's very similar to this, similar to what we did. Three forces act on a particle in equilibrium in the horizontal plane. Find the size of the unknown force F and angle theta. The key in these problems is when you are given that an object is in equilibrium, you consider horizontal equilibrium and vertical equilibrium and do what I did, equate upward forces to downward forces, rightward to leftward. Yes, it is in your book, but I'm not sure of this. It's in my book. This is chapter 3, end of chapter revision review exercise. What you see here. The page is 77. The page might be different for you. This is not there is no exercise. It's exercise 3. Review exercise 3. Find theta and f and tell me what you get.
Excuse me, miss.
Yes?
Miss, are we learning Lami's theorem?
No. This theorem is not in your syllabus.
Ah, okay, miss.
Miss theta is 42.8 and the force is 10.2 newtons.
Wait. Theta is
42.8.
42.8 and f is
10.2.
okay. Let's wait and see. Yeah. One more person give your answers, and if they tally, we'll accept it.
Miss, theta is 42.8. 42.8, and the other one is hold on. 15 sine 42.8 equals 15 sine 42 point. That would mean 10.2 for the force F.
Okay, that's correct. So I'll remove the book. These are your answers right here. Theta is 42.8 and F is 10.2.
Yeah.
Okay. Let's do an exam type question.
Miss, can you show the question for the last time,
Yes.
please?
Yes, sure.
Okay, Miss. Thank you.
Same exercise. Number 15. This is 2011 from the 2011 paper exam type question. Now I will tell you one more thing. This textbook has various different kinds of questions in its exercises. Unlike the pure mathematics textbooks, the exercises in the even the content in this book doesn't really match with the syllabus. Like Lami's theorem is in this. I mean, it's fine to learn, but we don't have time to learn extra things now, so we have to stick to our syllabus. And if you are doing questions from the textbook, mechanics textbook, stick to the exam type questions. There are so many different, various other. The flavor of those questions is different, so it's better to just focus on the exam type questions in your book. Okay. So number 15. Can you start that? Now, coplanar, there is a word here, coplanar forces. It only means that these forces act on one plane. They have to, right? Now, these forces that you draw here, they are all acting in one plane. You can't have forces acting like in 3 dimension. These are forces acting in 2 dimension, in one plane. Then you can resolve them into like that, into two perpendicular directions to find the resultant if you want to find. Like these, the forces that are in equilibrium for you are acting in one plane. That's the meaning of the word coplanar.
Miss,
Yes.
what are the answers for force and angle?
Let me see. Can someone say it? I lost that page here. Do I have it? Do I have it?
For the previous question, Miss,
Yes. Pardon, can you say it?
angle is 42.8,
Yeah,
force is 10.2.
Aditya there.
Okay, Miss. I got it.
You're trying number 15 now. Coplanar forces of magnitudes 58, 31, and 26 act at a point in the directions shown in the diagram. Given that tan alpha is this, find the magnitude and direction of the resultant of the three forces. Resultant. So you can simplify this diagram and resolve everything to these two directions. There is only one slant force, the 26 newtons force. If you resolve it to the two components, that would be a starting point. Just like you simplify an expression, you can simplify this diagram down to one force. It's like 3 terms are there, you can simplify to one term. Until you work on that, give me a moment. I'll check on something and come back.
Guys, are you still there? Tarindu? Malit? You here?
Yeah.
Nathan, yes, Nathan.
Okay. Guys, I just want to clarify my answers. I got 73 for the 73 newtons as resultant and 41.1 as the angle.
Okay, let me write it down here. I don't have a pencil. You got, say that again for the resultant you got.
73 newtons. I got 73 newtons.
And angle, alpha.
And I got for the angle
what
41.
what kind of a what in
I
what?
know, I missed the direction of resultant.
Yeah,
A positive direction.
like that.
Yeah.
In what direction it comes? Like a northeast or north?
Yeah.
Southeast or southwest?
The direction which you drew it.
Okay.
Yeah.
And is this the angle you are giving me with the horizontal?
Yeah.
Uh-huh.
Yeah, that's fine.
Yes,
That is 41.1.
Okay. So if I give capital F for the resultant, F is this. Is this
Miss,
right?
is
So
it okay if instead of F I wrote R?
yeah, R is okay. Resultant, R is okay. Hatfi,
Okay.
I will do it quickly. So you have 58 this way, 31 this way, 90 degrees there, and you have 26 angle tan alpha. They have given tan alpha equals 5 over 12. Now they have given you tan alpha, but when you resolve this, you are going to be needing cos and sine. Cos alpha and sine, you're going to need cos alpha and you're going to need sine alpha when you resolve, right? So let's first find those two here. When they have given you tan alpha of an angle, now I'm drawing a little right angle triangle for this to put this information in. If tan alpha is 5 over 12, that means I can draw a right angle triangle whose opposite side to alpha is 5 and whose adjacent side to alpha is 12, which means my hypotenuse must be 13. I think so, 13, no? Then sine alpha is 5 over 13, cos alpha is 12 over 13. I'm going to need this. So you do it in a little bubble and keep, because you are going to be needing that. Now, in order to find the resultant, if I simplify this diagram, this is already in vertical direction. I don't do anything to it. This is already in horizontal direction, 31. The 26, this force, I will split into two components. So I'll get one in that direction and one in this direction, right? This would be 26 sine alpha. This would be 26 cos alpha, right? Actually, you get it? So 26 cos alpha means, I'm just simplifying everything here itself. 26 times 12 over 13, that gives me 24. And this is 26 sine alpha means 5 over 13.
That would be 9.99. I got 9.999.
Okay, so
I
if
mean,
I,
I didn't simplify it. I didn't simplify it.
here are my forces. Now
Okay.
I can simplify it further to, I'm going downwards, or let me go this way. Okay, this is same as, so I have 58 upwards and 10 downwards. That gives me 48 upwards if this is my object. And this way I have 31 and 24 altogether, that is 50, that is 55. They are right angles. So all these got simplified to 2 like that. Now I can use Pythagoras theorem. So my single force that goes in between, and my angle could be like that. This is square root of like that. And theta is tan inverse the vertical force 48 divided by the horizontal force 55, y over x, whatever that is, whatever this is.